All right, I'm gonna go ahead and do the second half of the final exam review, starting with number 14. So it looks like here we're trying to find the freezing point. So we have the important information we need here. We're given the constant for the equation. Remember, the equation would be the change in freezing point is the freezing point constant for water times the molality of our solution. So we have Kf, so it's just a matter of figuring out the molality, and we have the information that we need. The only thing we need to say here is let's go ahead and assume that 1270 milliliters of water, but that's 1270 grams or 1.27 kilograms, which will be eventually in the denominator of our molality determination. And then we need to change our solute grams into moles. So it's 80 grams of glucose times 1 mole over 180 grams. So we can call that 0.44 moles. And that's the solute. So now we're ready to solve for our molality, right? It'll be those moles, 0.44 divided by the mass in kilograms of the solvent. So 0.44 divided by 1.27, that gives me 0.35. And now we can plug that in. So now we'll say delta TF equals 1.86 times 0.35, and that gives me 0.65. And so remember, it's a freezing point depression, so that means we're subtracting it from the normal freezing point. So since normally it would be 0, that means the new freezing point is negative 0.65. So not a whole lot of solute, so not a whole lot of effect. All right, let's go on to 15 then. So here it says a mixture is prepared by dissolving 35.5 grams of sodium chloride in 285 milliliters of water. If the vapor pressure of water is 23.8 torr, what is the vapor pressure of the solution? So now essentially we're figuring out what the vapor pressure lowering is caused by the addition of the solute. So we'll take our 35.5 grams of sodium chloride and we'll need to change that to moles. And periodic table will tell us 58.44 grams. So that would give me 0.607 moles. And then I need to change the water to moles. So let's call our 285 milliliters again. We'll say that's 285 grams. Change that into moles. So for water, we'll use 18.02. And that gives me 15.8. So now we can solve for the mole fraction of water, which will be 15.8 divided by 15.8 plus 0.607. So for the mole fraction of water, I get 0.963. So now 96.3% of the particles are water, so the new vapor pressure will be 96.3% of what it originally was. So now we'll say the vapor pressure of the water will be 0.963 times the original pressure of 23.8 torr, and that's 22.9. Ran out of room there a little bit, but hopefully you can read that okay. Okay, on to 16. This is just a simple Q equals ms delta T or mc delta T, whatever you want to call it. And we have everything we need here. It tells us that there are 12 grams of sample. The specific heat of this sample is 2.15. And the temperature change we're trying to achieve looks like it's 125. And for this, I got 3225, which I guess I should just report as 3220 from the odd even rule and 3 significant figures. All right, let's see. 17, this is one of those where we have our two metals in contact and they're going to meet at the same final temperature. So let's see, iron is at 25 Celsius and nickel is at 78. So let me write the heat that flows into the iron equals the heat that flows out of the nickel. And we'll just write a Q equals ms delta T for each of them. Remember, we're going to keep that variable T final in each case. Okay, so how's this going to look for the iron? It's 8 grams of iron. Specific heat of iron is 0.46 joules per gram per Celsius degree. And then for delta T, we'll write T final minus the given T initial of 25. And on the other side, negative sign, and it's 12 grams. Specific heat of 0.54, and the T final minus the original temperature of 78. So we can tidy things up here. So on the left side, looks like it'll become 3.68 TF minus 92 equals negative 6.48 TF plus 505.44. So now we can group like terms. Let me put the TF terms on the left and I'll get 10.16 TF equals 597.44. Dividing both sides by 10.16, I get TF equals 58.8 degrees Celsius. So that makes reasonable sense because it's between the two initial values. It's leaning a little bit closer to the nickel. That makes sense because the nickel had a greater mass and a higher specific heat value, so that seems pretty reasonable. Okay, 18. So kind of a mini Hess's law type problem here. We're given two equations and we want to find a way to add those together to get the desired equation. So the simplest thing to look at here is somehow I need 2C on the product side. The only source of C is here on the product side of the second reaction. So immediately I know I'm going to have to multiply that reaction through by 2. In the same way, I can see that I need an A in the overall reaction, and the only source of A is the top reaction. So that one I'm just going to leave as is. And so now in the simplest way, I can just add these together. So we'll make it A makes B for plus 55. And then we'll make the other one 2B makes 2C, and we'll double the value plus 46. So now the 2b and the b are on opposite sides, so the b can cancel with the coefficient, and that'll give me the correct equation. A plus b makes 2c, and when we add that together, it looks like we get 101. So for this desired reaction, it's positive 101 kilojoules per mole. So kind of slightly different problem, but the same approach. You're looking at your target reaction and trying to see what you need to do to the other reactions to make them match up. Okay, on to some more thermo stuff. So here I have the equilibrium constant, and I want to know the Gibbs free energy change. I guess this equation should say delta G naught, so we know to use 298 as the temperature. So we have everything that needs to go here. R is 8.3145. T, like I said, will make it 298. And then natural log of 2500. So the temperature should have been given. I didn't put it in there, but the temperature should have been given to make it clear, or I should have used delta G naught. Either way, when I calculate this, I get negative 1.94 times 10 to the 4th joules per mole. We can change it to kilojoules if we want to, doesn't really matter, but then that would be negative 19.4 kilojoules per mole. All right, on to number 20. So this is using the definition of the Gibbs free energy, right? We know delta G equals delta H minus T delta S, and it's basically telling us about the transition from non-spontaneous to spontaneous. And in this case, it's saying what is the minimum temperature to cause the reaction to be spontaneous, given that it's non-spontaneous at room temperature. So the plan is the same as it's been. We set delta G equal to 0 because that's the transition point, and that gives us delta H equals T delta S. In this case, they're asking us to solve for temperature, so it would become T equals delta H over delta S. So T would be, and we need to match the units, right? So the enthalpy is 45 kilojoules, or 45,000 joules. And then the entropy, already in joules, 85 joules. And it's joules per mole and joules per mole per Kelvin. Let me add that. And that'll give us a temperature. When we do that division with two significant figures, we should get 530 Kelvin as my answer. So that tells me that any temperature above 530 Kelvin will make this reaction spontaneous. That's what the question was asking us about. Okay, looks like one more thermodynamics one and then one voltaic cell problem. Okay, let's see what's going on here. Enthalpy of fusion, so that's the energy associated or the heat associated with melting ice and turning it into liquid water. It's 6.01 kilojoules per 1 mole, and it's asking what would the energy be to melt 100 grams of ice at 273. Let's pretend there's a decimal after the 100 so we can have three significant figures. And now looking at this one, we can calculate the value. So we know what it is per mole, but we don't have 1 mole, we have 100 grams. We need to change that to moles first, so let's do that. So 100 grams of water, again I'm buying myself 3 sig figs with that dot, 1 mole of water over 18.02 grams. That gives me, we'll call it 5.55 moles of water. And so now we know if it's 6.01 kilojoules per 1 mole, but I have 5.55 moles, I can just multiply. And it tells me the cost will be, we'll call it 33.4 kilojoules. And then in part B, now it says determine the entropy change. So now that I know delta H, I can figure out delta S. So remember, the real definition of entropy is based on considering the ratio of heat flow to the temperature at which the heat flow occurs. So we're kind of restricted to only calculating this for constant temperature processes like changing the temperature, changing the phase of a substance. So 33, I'm just going to make it in joules now, 33400 joules. And we're doing this at 273 Kelvin. That's what it reminds me of in part A. And so the ratio of these is all I'm looking for. And 3 significant figures, we get 122 joules per Kelvin. That's the entropy change that is associated with melting ice. It's a positive number, that makes sense, right? Surely changing solid to liquid will give us an increase in the entropy of the system, so there's a positive entropy change. Okay, last one. Looks like we're answering all sorts of questions about this redox equation. So we're going to balance it under acidic conditions first. Let's do that. I'll separate the two. So I've got iron 2 making iron 3. And then I've got MnO4 making Mn2 plus. Okay, let's do the one on the left first. That's the most straightforward. I just have to add an electron to the right-hand side to make the charges on both sides +2. All right, now for the other side, the right side needs 4 additional waters immediately to make the oxygens balance out, and that unbalances the hydrogen, so I need 8 hydrogens on the left. Now I need to add electrons to balance things out, and right now as it stands, the left side of the equation is +7 and the right side of the equation is +2. So that means I'm going to need to add 5 electrons to the left-hand side. And now we're fully balanced. But now what I see is I'm going to need to multiply the left-hand side equation by 5 to match the electron flow. So it becomes 5 iron 2 makes 5 iron 3 plus 5 electrons. So now we're just going to add these together, and I can just scoot the iron one down here. 5 iron 2 makes 5 iron 3 plus 5 electrons. And immediately we know our electrons are going to cancel. And now we just need to copy it all over again. So 8H plus permanganate plus 5 iron 2 plus makes manganese 2 plus 5 iron 3 plus 4 waters. Something we should make a note of here is our N value based on the electron flow on each side of the reaction. If we need to calculate delta G or K or anything like that, we would need to know that N value. Okay, now it says determine the value of E naught for this reaction. And in order to do that, I just need to look up some values on our table, and that'll help us figure it out. We can do that real quick. So we know iron 3 to iron 2, if I look it up on the table, I get 0.77. And that's the opposite of the reaction that I'm doing. And then for the other one, I'm just going to write MnO4 minus to Mn2 plus. I know there's all those other parts to it. That one is 1.51. So we need to flip the top one to change it from a reduction to an oxidation. So this will become 1.51 plus negative 0.77. And then that value will be our E naught for the reaction overall. That should give me plus 0.74 volts. Okay, now in C, it's asking me for delta G naught and K. Delta G naught is just negative NF E naught, so that's where I need the N value. Remember, that's 5 moles of electrons. Faraday's constant 96485, and then the E naught value we just calculated 0.74, and that gives me negative 3.57 times 10 to the 5th joules. And then we can use that to solve for K, right? K equals e to the negative delta G naught over RT. That becomes e to the 3.57 times 10 to the 5th divided by RT, 8.3145 times 298. That becomes e to the 144 power. It's okay to leave it that way, but if I am able to calculate it, we would get 3.76 times 10 to the 62. So a really large equilibrium constant value to reflect the fact that this is a spontaneous reaction. Yes. And the reaction goes very far towards completion, so it's a really large K value. Okay, the last question here, it's giving us a Nernst equation type problem, and we know that because we're changing the concentration of one of the components. So now we need to kind of go back and see what the equilibrium constant actually looks like for our overall reaction. So let's scoot up to part A. And so now on the reactant side, the important things are the permanganate and the iron 2. And on the product side, the manganese 2 and the iron 3. Nothing else is going to show up in the expression. So it'll become concentration of manganese 2 plus times the concentration of iron 3 to the 5th power divided by the concentration of permanganate, divided by iron 2 to the 5th power. And it's telling us about one change just to the permanganate. Everything else is going to be 1, So in this case, it means our equilibrium constant will be 1 over 0.005 because everything else stays the same, and that's 200. And that's K, but really this means it's our Q value. So now that we have our Q value, we're ready to use the Nernst equation. The equation just says E, the non-standard voltage, equals E naught minus RT over NF, natural log of Q. So I'll need my E naught value from the previous step, which was 0.74 volts. And then for everything else here, 8.3145 times 298. Remember that N value is still 5 for the moles of electrons on each side of the reaction, times Faraday's constant, the charge on a mole of electrons. And this will become the natural log of 200. So after cleaning all that up, the second term becomes 0.027. So the new voltage becomes we'll call it 0.71 volts. So not a huge change by modifying the molarity of one of the components. That's an interesting point. You really do need to drastically change molarities to observe a substantial change.